All right, brilliant. Thank you, everybody. Yeah, sorry I can't be there. It's a real shame and not what I expected to be here, but here we are, and we'll make the best of it. So hopefully this, the last talk of the day, it's not going to kill the energy in the room being remote. So yeah, I'm Martin. I'm from the TrustFabric team at Google, and I'm here to tell you about verifiable indexes. So first, we're going to go through like what problem verifiable indexes solve. So it's kind of been hinted at a few times today. There's a bit of a usability problem with large logs, and this usability problem kind of gets in the way of realizing the full benefits of security that we can get from a transparency ecosystem. But fear not, the solution is a verifiable index. And then so I'll go and explain what the verifiable index is from the user's point of view and how it can be verified. And finally, I'm going to spend a bit of time trying to encourage people to get involved. So we've got something that works right now, but it's about making it real in the real world. And so that's why I'm kind of excited to talk to everybody. So what is the usability problem with transparency logs? And basically, it's how hard it is to find your own stuff in them, right? So if you're a domain owner, I mean, it's kind of what Rasmus has just been talking about here, right? If you're a domain owner and you want to find all the certificates for your domain in a certificate transparency log, you've got a lot of other people's certificates to go through. In fact, the vast majority of them, no matter who you are going to be other people's certificates. And that's not just the case with certificate transparency. Other large log ecosystems also have kind of problems like this. So for example, Filippo was talking about SumDB earlier, and that's an example I'll come to a few times through this presentation. But yeah, if you're a module maintainer and you want to find usages, all the statements that have been made about your module in the logs, then again, you've got to go through lots of the people's stuff, and SigSum and SigStore with signing or identity transparency also have this same problem. So, all right, it's hard to find your stuff in there, but why is that even a big deal, and why should we care? I think let's take a little step back and just kind of remind ourselves what the point of transparency is. And really, the point of verifiable logs is to make sure that we all see the same view of data, and that's what we call transparency. And just because something is stored transparently doesn't mean that it's actually going to be seen, and that's a problem, right? Like, it's the ability to see any bad things in there, notify the right people, and take action against them that actually fixes any badness happening in the system, much like weeding kind of a garden bed, for example, right? So in certificate transparency, who can tell if a certificate for your domain was legitimately requested? And I think the answer is you, really. Other people might be able to have a best guess, but you as the domain owner are the only person who can authoritatively say that. So in certificate transparency, it needs to be easy and it needs to be secure for you to find the certificates for your domain. And the same goes for all the other ecosystems too. So how are users finding the data in logs today? And I think a large majority of people aren't, and maybe that's because they don't know that the logs exist or how to go through them, or maybe it's just because it seems like a lot of work. But either way, it means that if people aren't looking, the people who can authoritatively say whether something is good or bad aren't looking at that stuff in logs, and that means malicious behavior might not get detected, and that's obviously bad. Now, a step up from there is people using indexes of any kind. Now, there's a lot of unverifiable indexes in the world at the moment, and using those is obviously miles better than not doing anything at all. But it's unverified, right? We've had verifiable data structures to store the things, but at the point of use not having them, that's obviously, it's unfortunate. It means that entries could be hidden from users, whether maliciously or through bugs, and users would be none the wiser. And then finally, like Rasmus has just been talking about this, how can you do it verifiably? Well, the only way to do that is to download the whole contents of the logs onto your machine and then kind of go through them. And that's what Silent CT Monitor does, and it does it nicely and silently. But it's it's expensive somewhat for the user. You've got to have the infrastructure to be running this, and Prometheus or whatever. Yeah, but really, it's expensive for the log ecosystem. We've talked a lot today. I think it's been a recurring theme about how log serving's expensive. Imagine if every domain owner in the world tomorrow just went, "Oh yes, Silent CT Monitor sounds great," and launched it. We're going to have a pretty expensive tomorrow, aren't we? But what if we could get the best of both of these worlds, right? So we could get the benefits of the index, but we could get the verified parts, and maybe we could call it a verifiable index. And so we can, and that's what we've called it. And yeah, the users can basically get fast lookups that are lightweight. They just get in the contents that they've asked for, and it's verifiable all the way to their machine. The log benefits, because not every single user who's verifying the contents of the logs is scraping the whole contents of the logs. They serve the log once to the index, and the index serves it to the people, and then the people can come and just get their parts of the log. And the fact that this should make it easier and more reliable to make sure that there's no badness there raises the security property and kind of makes everyone safer. So let's go and have a look at kind of what this looks like from a command line point of view here. So like at the heart of it is basically, like I said, like the index in the back of a book. You give it a keyword, and then it tells you all the places you can find stuff about that keyword. So here's an example that's based on the GoSum database, GoChecksum module proxy. We're looking for the module github.com/transparencydev/Tessera, and it says, hey, here's all the locations you can find that. And you'll have to trust me, this is verifiable, or you can look in the code. And so this is all verified, but I mean, okay, that's the heart of what the index actually is, but it's not massively exciting or compelling, I don't think there. So let's take it a step further and make it so that if it knows where the input log is, it can dereference these pointers effectively and get you the content from the log. And that's what this does. And you can see here that the module name we've searched for Tessera comes up in all of the leaves. So the index is at least working there. And then along next to the module name, we see the version name. And then alongside that, there's a couple of hashes. So that's SumDB's view of the world. And we've now verifiably pulled that down to our machine. But I still, like, we can go a little bit further again, right? Because if I give this to somebody who's a Go developer and says, there you go, this solves the problem that you've got, they'll say, I don't have a problem that looks like that. So this, I think, is a little bit more compelling, or maybe fully compelling. I think this is quite cool. So this meets the Go developers where they are, and you have this SumDB verify command that you point to a git checkout of your Go module. It inspects there, finds the Go module file, and finds the module name, does the lookup that we've just seen on the last slide, and then it's got all of that content verifiably locally, and then it can inspect the Git module, the Git repository, and look for the tags that are there. And if it finds the Git tag, then you get the first of those ticks in each row. Then it checks that the Go mod file matches the hash that SumDB had, and then you get another tick, and finally produces the zip file and checks that all the source that your users have depended on matches what you've got in your Git module. So yeah, that's it. And I think this is really cool. This like closes the loop, right? So what you have published as a Go, as a binary, author, is what your users have downloaded on. It's all verifiably checked on your machine here. And it's all done without scraping the whole log contents locally. We're querying the verifiable index and checking it locally. And I think another cool property just to notice from this, it kind of hides away all of the log and the index stuff. The data structures themselves become transparent, and we've got a real kind of user experience that's focused on where they are rather than the crypto stuff. So that's pretty cool. And I think we can imagine, hopefully there's people in the room imagining, I could build a tool like that, like Silent CT Monitor could use this, for example, or other ways of doing it for CT and for identity transparency as well. And I'd love to work with people. That'll be one of my appeals at the end. I'd love to make those a reality, but I'm going to need other people's help, I think, to do that. Okay, so hopefully that's compelling, and people are now seeing, like, okay, yeah, that seems good. That solves a real problem, and I can see that we can build real tools on top of it. But an appeal to magic that it's a verifiable index without explaining how it's verified is a bit too much of a leap, I think, for a conference like this. So let's have a look at how it could be built, right? So a URL like that, where you basically pass in the key or a hash of the key, and that's what you're looking for, and then it returns all of the pointers basically into the input log. Great, as a basis, that's kind of what we have in the world today with the unverified indexes, but it's not verifiable. So how can we make it verifiable? Well, we'll just commit to the keys and values in a cryptographic data structure, so that the key is the sort of path through the tree, and then the value gets hashed at the bottom, and then you can get an inclusion proof. So you get the pointers back, you get the leaf node, and then you get the proof through that, and you get the verifiable index root in there as well. So, okay, great. Now you can do an inclusion or a non-inclusion proof, but it doesn't really help us if you could give everybody different hashes and basically it's split views. But hang on, split views, we know how to solve split views, don't we? So how do you do it? You stick it in a log, and then you get a response that looks like this. And this is the final response. In addition to all the stuff we had, we moved the verifiable index into a leaf of the verifiable index root goes into the leaf of a log, and then you get an inclusion proof and a checkpoint that's witnessed for that. And now you know that it's not that it is fully verifiable. And we'll come back to how that's verified at the end. But I kind of want to address a bit of a elephant maybe in the room, or things that making people uncomfortable, that there's like quite a lot of data structures appearing. So the first one of these we already had. The input log there in blue is the log that we're indexing. The verifiable index in red is a sparse Merkle tree committing to the keys and values. And then finally, the output log in a cyan is it's there. It has all the index roots in there. It prevents split views, and it makes sure that we've got an audit trail. And we'll get onto how the audit kind of how the construction of that verifiable index can be verified afterwards. But let's go back to the start of the whole kind of journey, right? You've got an input log and you want to index it. How are you going to do that? So let's consider it like the index in the back of a book. If somebody gave you, a book and said, create me an index in the back of this book, how would you do it? Well, you take each page and you identify what the keywords are on each of the pages, and then you know what the page number is, and you put those in the index at the back. Sort of job done, right? And that's very similar to what we do here. This map function takes a leaf entry, and then it parses it, does whatever's needed in the business logic to determine what the keys are that should point to this, and then it returns a hash of those keys. And that's kind of it. Some of this stuff might change. The little icon in the top right there is sort of pointing at like there's things here that may well change. So for example, this is returning a hash of the keys at the moment. Maybe we should return the keys themselves directly, which would allow us to build prefix trees and other kinds of data structures. But at the moment, they're fixed size hashes. That's one of the things that we can kind of change afterwards, with discussion. But the important property to take from this is that it's deterministic, because that will impact whether it can be reproducibly built. And then, you don't have to return any keywords. You can return nothing if some entry is not particularly interesting, or you can return multiple keywords as well. So, for example, in CT, this would parse out the X509 certificate. It would extract all the DNS names and the IP names from there, and then return the hashes of them. And then the verifiable index code takes care of updating those into the index. But what is the index itself? Well, the version we have at the moment is a sparse Merkle tree. It's actually compatible with AKD. It's fully ported their code across into Go, which is great. That said, we're looking at other data structures at the moment that might allow us to go quite a lot faster. So these things, again, might change, hence the icon there in the top right. The values are just uint64s, they're pointers into the input log, and the leaf hash can be deterministically determined from the values. At the moment, we just kind of append them all together with a big endian encoding and then hash it, but that could be a Merkle tree or something else if somebody has a compelling motivation that we could change that. And when we update the verifiable index, we do so atomically in batches, and making sure that the index state that we're serving always matches to an input log checkpoint. And that's a big part of the verifiable story, and we'll have a look at verifying that later on. Once we apply that batch to the verifiable index Merkle tree, and we roll it all up, we'll get a new root. We put that root in the output log, and then we get the new output log checkpoint, and that gets witnessed, and that holds us accountable to that, and we can't go back on it. And then that's what gets used in that lookup. Quickly, we'll take a detour via the output log. I said that it has the verifiable index root hash in there, and it does. It also commits to the input log checkpoint that we used to get there. And I think that's really cool, because those of you that know me know that I love my claims. And this is a falsifiable claim that can be made here, right? The index operator makes the claim that if you index a log, this input log here, that with this size and this root hash, with the map function we know about, then you will end up with a verifiable index with this root hash. I mean, that's almost clear how we'll falsify that, but we'll revisit that in a little bit. I want to first come back to how the client basically verifies this proof that we talked about. Now that we know about all of the data structures and how they're related to each other and what their purpose is, let's walk through how the believer is going to verify that this because it's kind of a lot of stuff that may be a bit hard to unpack, right? So it's all about checking the corner of the world that your believer cares about, right? So maybe you with your domain, that there's a cryptographic proof that ties up to something that everybody agrees about, which is the output log checkpoint. So we'll check that the output log checkpoint is signed and witnessed appropriately. Cool. And then we check the inclusion proof within the output log to get the leaf. We know what's in the leaf. It's a verifiable index root as one of the things. So we can pull that out, and then we can use that along with the proof that's there to check that the values we're going to rely on are committed in there. And at that point, we've convinced ourselves that our little corner of the world is completely tied nicely into the thing that everybody's witnessed and is agreeing on. So we're all on the same page. So the only thing now that could mislead us is if the verifiable index itself was constructed badly. But that's the part of the verifiable index, right? So let's check how that's guaranteed. It's pretty simple, actually. So we've already discussed how you build the verifiable index from the input log. And we've already shown that the output log contains these falsifiable claims, right, with the input log checkpoint of a verifiable root hash, the index root hash. And so anybody else with enough compute power and interest can come along, take any one of those claims, or all of them ideally. You get the input log, make sure that it matches that input log checkpoint, and then you build the verifiable index yourself. And if you've got a different root hash at the end of it, then you've got a reason to start a pretty tricky conversation, but probably they'll match. This is an important part, by the way, of why it's so important that that function earlier was deterministic, because obviously if it wasn't, then you might end up with different root hashes. Okay, so that's the little walk through how all of that kind of works. Now I want to kind of, try and invite people to come and get along, get involved, join in with what we're doing here. And how can you give or receive the gift of fast lookups to your loved ones this Christmas? So the prototype is there in transparency dev /incubator in GitHub. And in there is a library that does the index construction. You basically provide it a map function and the input log, and it does everything else sort of for you. You just crank the handle and say, build it again. And there's also some client library code that checks all of those proofs that we looked at that big chain earlier. And then you can run your own applications with that. So the full source for the GoSumDB one that I showed earlier for the SumDB verify command is there. So all of the code for building the verifiable index from SumDB log itself, and the client tool that checks your Go repository is all legit, and all the Git hashes match with what's in SumDB. And there's also a demo in the log and map demo, it's called, which checks, which basically shows how do you run your own log. It uses Tessera, put your own stuff in, whatever that is, and then how do you run a map, a verifiable index alongside that with your own map function to extract all the stuff, and how do you serve them all. So there should be something in there that you can adapt for whatever you're wanting to do. So possible changes, I'm only going to whiz through this actually because there's not a lot of time. There's a lot of stuff, as you may have seen while we're going through the deck, that may well change, including like how the core verifiable index itself, the data structure that's used there. One of the things that might be cool to do would be implement the map function using WASM, so that we could have different implementations of the core library. It's the verifiable index library in different languages, but still be able to port this map function across without constantly firefighting small differences in, say, libraries and how they implement X509. It's a shame that I'm not there in person, because I really was looking forward to chatting to a lot of people about this and how we can make it real for CT. The biggest hurdle is that the verifiable index at the moment it's a one-to-one. So you've got one log and you get one index. Obviously, that's going to get quite messy for CT, where there's like quite a lot of logs from different operators and shards. So what if we can find some way to make the verifiable index be kind of have multiple logs kind of fed into it and still maintain that verifiability. I think that's possible, and we've got some ideas for how that can be done, although it obviously makes things a little bit trickier. But that's an important part of, I think, what could come next. And then, yeah, get involved in other ways. So obviously experiment with the demos. If you're a Go developer, please try out the SumDB verify thing there. Deploy your own verifiable index. And here's a last minute slide. Hayden sent me this morning. He's there with you in the room right now. And yeah, basically within an hour wrote his own verifiable index using the stuff in there. So it's definitely possible. Yeah, take a look at the design and then come and get involved with, yeah, on the GitHub repo with issues and comments and PRs even, and then join us in the Slack channel where you can, we can chat about this afterwards. And so, yeah, thanks everybody for turning up and listening. Sorry I can't be there with you, and everyone that got the verifiable index to the point where it is, and whoever asked me questions for being kind, because it's been a long day. I've got a sore throat, and yeah, this might be difficult over remote, but that's everything I've got. Thank you.
A round of applause for Martin, please. Now, I've been assured he can hear us. Not if you can hear us.
Yeah.
Yeah, absolutely. So we can have some questions. Does anyone have a question for Martin? We have one over there. I will come. Da, da, da. You can have to wait while I run across the room. I don't know if he thinks.
So this is very exciting. I was wondering if you'd given thought to map functions that can collide, as in, like, say your transparency log is storing updates to a dictionary. So at any given time, there is a newest value in the dictionary. So in this case, this map function would collide with itself occasionally. And so if you were to query the verifiable index, it could very reasonably return a value and say, oh, here it is in the tree, but it might not be the newest value in the input log. Have you given this any thought? Do you see any solutions to that?
Yeah, I do. In fact, I used to have an implementation quite a long time ago that did do this. The verifiable index is one of the things I didn't have time to get into. It's like a Pareto principle. It's sort of 20% of the complexity that gets 80% of the value, I think, in the space. But what you're pointing at is the sort of 20% that's left. The reason the verifiable index is kind of neat is because it just has all of the indexes there. So you just keep appending to it and you don't have to worry about this idea of latest. The map function name comes from basically the MapReduce framework, and the other part of that, the reduce function, that can take a bunch of values and then squish them together and come up with another value, maybe just one of those ones there, or synthesize something new that comes in, is the missing part, I think, for the question that you're asking. And that's explicitly, the reduce function basically here is built in, and it just gets the leaf ID, the index, for everything, and then just concats them together. But yeah, you could make that also be configurable, and you could still keep it as I think a verifiable data structure. It's just a little bit more complex because various reasons. But if this is something you're interested in, then I'm definitely interested in, this is what I see is like, get the verifiable index out and then move on to something that's more general afterwards.
Wonderful, thank you.
Hey, so it has happened in the past that certificates have been logged in CT with ambiguously incorrect X509 encoding. So I was curious how the system handles that problem, where maybe you can't verify a certificate, but it's not clear that nobody else can verify it.
Yeah, this is the complexity of writing. I sort of skipped over that bit, but it is the complexity of how do you write the map function, I think, for CT. And I think something is definitely doable there. One option is that you could have a special places that the key hash that you return could basically encode in its pre-image something about like weird certificate for, and then put those all in one place for humans to also do some manual review over, or other ideas welcome. That's kind of why I'm a Go developer. I spent a lot of time in this ecosystem, so I can talk somewhat authoritatively to it, and that's why I focused on the sort of proof of concept being there. And I'm kind of appealing, like, I know enough to kind of get through a lot of CT stuff, but like for stuff like this is why we need top CT experts who know and care about this stuff to kind of get involved in helping us craft the perfect map function.
Okay, hi Martin.
Hello, Rasmus.
Hi. How do you see this unfold in CT? So should there be one verifiable index per log, or should there be one verifiable index for all of the logs combined? And what are the trade-offs?
Yeah, I mean, so what we have at the moment, you could do an index per log, because that's what the data structure sort of supports, right? But I think you've definitely made the problem a lot better, because rather than users having to scrape dozens of logs in their entirety, you now just have to do lookups in dozens of indexes. But it still feels like maybe you could just have gone that little bit further, right? And make it so that it's just one index, but it makes it a bit more complicated. I mean, at the end of the, yeah, I think the things that you put in the output log wouldn't just be a single like root hash and checkpoint. It would be like a root hash and then multiple checkpoints for all of the logs that are in there. And then you need to update the data structure instead of just being a uint64, like, because instead of just being a pointer that's just assumed to be at one log, you would need to provide some context about which log you're pointing to as well. And I think those things are solvable. Like, it doesn't keep me up at night, but it seems like it's a reasonable amount of code, and best discussed as a sort of a group of people kind of to get to a solution. So again, get involved and help us work out how we do that.
It's really cool, Martin. In terms of what you're writing to disk, it sounds like you probably only need to write the new kind of witness for the top of the MPT. So presumably a lot of this is done in memory and it's pretty fast, or do you sort of, how's the performance, I guess is the question.
Yeah, well, so that's one of the things I said. The version that we have, so Filippo's ported the AKD implementation across to Go, and that has two implementations. One of them's memory-based and is unsurprisingly fast, and the other version uses, I don't want to misrepresent it, I'll let Filippo explain, but I think it's basically recursive SQLite, and that version is not really fast enough to ingest the CT log from when I tried to do this one. Which is why we've been working with Russ Cox as well, trying to come up with a newer version that is super fast and can be written quickly to disk, and that's sort of something in the pipeline at the moment.
That sounds really cool. Really interested in that.
From the auditor's perspective, it seems easier to have one index per log, because otherwise, if you have a data loss of one of the logs, you wouldn't be able to verify the index.
Yeah, exactly. This is sort of what I mean about some of the complexities with it. I think, yeah, like for example, if one of the logs has some kind of a split view type of thing, and then, it will be a fatal error for the log, but then the index has kind of gone past the point where effectively policy says, no, it should have been 3,000 leaves before that, where the split view was detected, and that's the frozen endpoint of it. Things get a bit gnarly, and that's the kind of problem. Like, for example, we need a bunch of people who are experts on CT to see how we solve this problem. Like, it's well solved for a single log to a single index, and the multiple logs to a single index. I feel like it's possible, but it gives me the willies, and we just need to have a conversation and work out, it might take a while to get there, maybe a few failed iterations, but I think this code is pretty easy to kind of iterate on. So hopefully we can find people to do that.
Okay, I think we will leave it there because we are just about at time now. Thank you so much, Martin. It's been great having you here, virtually at least. For everyone who's here, Martin's been chatting away, like he's been watching the live stream all day. He's been very actively contributing to quiz questions. Remember, there's a quiz on Wednesday. So a big round of applause for Martin. Thank you for doing what you can to be with us. We all wish you were here and do miss you.
I wish I was there as well, but I'm here.